Here we are again. Welcome back. We're going to take a look at complex numbers, and I just can't resist taking a moment to look at this little cartoon. I is saying to pi, be rational. Hard thing for pi to do, isn't it? And the response, back to I, get real. Another thing, a little difficult for I. I is not real. However, both of them can add a little squiggly. Here we go. That will sort of get them there, won't it? Excuse me. I square is the same as -1, which is certainly a real number. And if this were representing all real numbers, we know at least some of them, not all of them, of course, but some of them will be rational. Okay, let's get on with what we mean to do today. We're going to solve equations. Ooh, that's good. Finally, we get to do something with this. Multiply complex numbers. Find conjugates. Oh, I love the conjugates. Remember conjugates. We have a sum and a difference. As long as the first term in the binomial and the second term in the binomial are identical, a sum and a difference, that is what we're talking about when we say conjugate. Finally, the most interesting part of today is, and the most challenging, is to find the reciprocals of complex numbers. Let's take a look at what we've got ahead of us, so maybe I can time us properly. Okay, we got quite a bit to get through. First off, we're going to look at something which I told you we were skipping, and we are skipping it. It's just, I can't resist at least pointing it out to you. Complex numbers and graphing. I want you to know what we're skipping. Graphing a complex number, instead of looking at x and y, we're looking at a real number axis and an imaginary number axis. If you want to know more about this, you can look in your textbook. We're going to focus today on 7-9, more about complex numbers. How would we calculate what this is? Well, we would have to use the Pythagorean theorem to do that. Since I'm skipping over that section, it might be wise for us to skip over this particular problem. Again, if you want to know more about it, come see me and we'll talk about it. It's also in your book. Adding complex numbers. Well, we know how to do this, right? This is an addition, so nothing is going to change in here. We're going to have 3 plus +3, which is equal to 6. A positive 5i and a negative 5i, which will give us 0. Right? The i's are disappearing here. The important thing to pay attention to is we were adding. I noticed a few people you're thinking about so much that you sometimes don't pay attention to whether you're adding or multiplying. Can we simplify this next one in number 2? We sure can. We can say that's the same as base I to the 4th power times base I to the 1st power. Remember, as long as the bases are the same, when you're multiplying factors, well, that's what makes them factors, you add the exponents. So we can take I to the 5th power and rewrite it like this, which is a nice thing to do because I to the 4th, we know from the chart we worked on last time, is the same as 1. 1 times I, except when we have a coefficient of 1, we don't write it. We just assume it. We know it. So that simplifies nicely. This one we're not going to do. because we skipped by 7.8 where we learned all about that. Here's something for you to remember down here. You already have this in your notes. The absolute value of x is the same thing as the primary, right, this is positive, or a principal square root of x squared. That's probably going to come up for us today. Solving for x and y. Ooh, a new wrinkle. So we've got x here, which is part of the real portion, and we've got y here, which is part of the unreal portion. Wow. So I can say that if these are equal, the real portion, 5x, is equal to the real portion over here. And I can say that the imaginary portion is equal to the imaginary portion on the other side. You see what's happening, don't you? We're going to be able to figure out x and y. X is equal to 2, and when we divide both sides by 2i, I divided by I is 1. 6 divided by 2 is 3. Y equals 3. Solving for x and y when you have a complex number. Let's think about complex numbers a little bit in terms of what they're equal to. Is 3 plus 2i equal to 2i plus 3? Well, here you have to remember the commutative property of addition. Its position, where it is located, will not change its value. So it can commute to the opposite position. So the answer here is yes, these are equal. Does -1 plus 1 equal 1 minus 1? Ooh, no. No, that's a different piece altogether. So we've got a -1 plus I is not equal to, and how else could I write this? I could write this as -1 plus I. These are definitely not equal. Okay, moving on. We're going to simplify these now. We're going to simplify by multiplying. We have to multiply the real, well, we have no real. We have to multiply the coefficients and the i's separately. So 2 times 2 is, and I times I is, oh, maybe you're already telling me -1. Of course, I squared is -1, so this is equal to -10. Down here we actually do have a real section as well as this. We're going to multiply these together. Well, sure looks like a binomial, doesn't it? This complex number is in fact 2 terms, just like our binomial. We're going to FOIL. And when we do, we get for our first term 6. And when we do our outsides, we get, now we've got 2 times 8, those are the coefficients. Remember that when we're FOILing, we're always ending up with 4 terms being added or subtracted together. Okay, so we've got 8, and it's positive. And what happened here? This, we have no I here, but we have an I here, so that's going to be a just I. Now we're going to do the inside. This is also going to be plus. This time it's 15. And again, it's just I. The last terms, when we multiply those together, this is where it gets interesting. Plus 20 I squared. Now, anytime you're getting an even exponent on I, you need to be happy, because that means we're going to be able to move it from being unreal or imaginary into being a real number. So we're going to end up with 6, and then I'm going to take care of this one here. I square is -1 times 20, correct? And right here, I've got like terms. They both have I to the first power, so those are like terms. When I add 8 and 15, I get I can simplify this even further, because now these are like terms. So I've got 6 minus 20, that would be minus 14 plus 23i. So when I multiply these two complex numbers together for my answer, I got a complex number. All right, let's try this one. Again, we're going to FOIL. Let's see. Oh, I don't usually do it that way. Let's go back to that. The first together, 1. The outside, -I. The inside, +I. And the most interesting one, oh, that's not going to be, sorry, I had to go back. So I did the first, and then I did the first, then the outside, -I. Then I did the inside, which was a +I. And this is what I was just working on. A +I times a -I will give me a negative, but it'll be I squared. What am I going to get out of this? I've got 1. When I combine these like terms, I get 0. It's adding a positive and a negative of the same thing together will always give us 0. And then I've got negative I squared, which is the same as saying subtract a -1. That will all together equal 1 plus 1 equals 2. Isn't that interesting? So when how could I miss this? These are conjugates. I bet you saw that. Those are conjugates. I was never going to get a middle term with conjugates. Well, think about our definition. We've got both of them start with 1, both of them end with I, and one is a sum and one is a difference. We were never going to have any middle terms. They cancel out. I could have saved us some time there. I can just hear you saying, Mrs. Turner, those are conjugates. Okay, we'll go on to the next one. Find the conjugates. Ooh, find the conjugates. Okay. Now, there's one thing that's kind of tricky about this. We have to remember what the form is supposed to be. When we write a complex number, we need to make sure the real is in the first position and the imaginary portion is in the second position. This becomes extremely important when we're dealing with finding conjugates. Finding the conjugates. So with a conjugate, it's actually not going to be equal, is it? We're just going to find the conjugate. The sign stays the same on the first one, right? But we go from adding the second, in other words, we go from adding the imaginary to subtracting it. So there we are. On this next one, I'm not equal, I'm just transforming it here into its conjugate. I've got the real first and the imaginary second. So I've got 3. Now the conjugate here will be an addition. So rather than subtracting the imaginary portion, add it. Looking good? Ooh. Now this one's tricky. Where is the real portion? I don't have it. Well, I can put a 0 in as a placekeeper. Go for that. And this is a positive, so it's going to be plus I. So what I've done is I've transformed this into a complex number by recognizing that 0 is the real portion of it. So now when I go to do, by the way, this one actually, that actually was an equal. Those do equal. Now I'm going to transform that into a complex number. So I'm going to start with the real, which doesn't change, and then instead of finding a sum, adding the imaginary, I'm going to subtract the imaginary. Now, I would never give you an answer like that. We don't bother writing the 0 when we've got sums. There we go. It's just, oops, how can I do that? It's a negative I. So the conjugate of a positive I is a negative I. This one is interesting. This one doesn't have any imaginary portion. So how do I find the conjugate of this? Well, I'm going to use the same technique we used before. I'm going to have something here for I, but it has to end up not showing as anything, so I could do that by multiplying I by 0. So when I go to do the conjugate, it's still going to be 7, but what am I going to do with the imaginary portion? I'm going to subtract it. So I'm going to subtract 0I, which should be pretty easy to do, right? So there we go. The conjugate of 7 is 7. The conjugate of I is negative I, and that's all because of their position in a complex number, where the first part, the real, is never going to change in a conjugate, and the imaginary, the second part, is always going to change its sign in a conjugate. Hope you like that. Okay. We're going to multiply these two together. What have I got here? That's right. You've got conjugates. So let's multiply them. We get our first together first. Let's see, 16. Because it's a conjugate, I know that when I do the outside and get negative 8i, and the inside a positive 8i, they're going to cancel each other out. So I can save myself that step when I recognize that I've got conjugates. So all I have to do is the first and the last, which will give me a negative 4i squared. You're going to see this a lot in this section, where I is going to be raised to a even, or sometime, anyway, greater than 1 exponent, which allows you to do something with it. So that's the same as 16. I square is a negative 1. Negative 1 times a negative 4, same as 16 plus 4. Don't you love it when you have an expression as complicated as this and you can get it down to something as simple as what we see here? This is some of the power of mathematics. It can take something complicated and simplify it for us so that we can understand it better. Here I've got conjugates again. Let's see. Because it's conjugates, I don't have to worry about doing the outside and the inside. I'm only going to do the first and the last. So the first becomes x squared. The last becomes a negative, right? A positive 1 times a negative 1. Y square. I square. I square is equal to a negative 1. So I'll simplify this. X square plus y square. Remember that in your answers, when you've got I, you are never leaving I with an exponent. Oh, my handwriting. Well, good thing I'm speaking, so you know what I'm talking about. Greater than 1. You can always simplify it. Just need to use that little chart that takes you from I to the first power to I to the fourth power. The really good news here, really good news. We've been able to factor a difference of squares for quite a while. Now, using complex numbers, you are going to be able to factor a sum of squares. So we could go backwards from having the sum of squares to these factors. I know they're a little weird looking with their complex parts, but we know how to do it. We just need to practice doing it in order to get good at it. Look at us rolling right along here. I'm so happy. We're maybe going to make our new goal. Here we're going to divide. Find the reciprocals of complex numbers. Reciprocals of complex numbers. Reciprocals of complex numbers. How are we going to do that? What would be the reciprocal of this? Well, you know, I'm going to give us a look ahead here. How do we go from here to this answer? This is actually reciprocal of that. Let's see how it happens. So, put my pen back. We know the reciprocal would be I Okay, dividing, and then we are going to find reciprocals of complex numbers. We're starting with the dividing piece. Yikes. Ooh, forget about putting an equal sign in there yet. I want to rationalize my denominator. So I can rationalize an I pretty easily. I just multiply it times itself. That will give me 2I over I squared, which is equal to 2I over negative 1, which is equal to negative 2I over a positive 1, which I would just write as negative 2I. So when you're dividing and you've got a complex number or imaginary number in the denominator, first rationalize your denominator. See how nicely that worked out? On this one, Okay, goof coming up. Let's see if you can spot it. We've got my old friend in the denominator here. If I don't use conjugates, I will have a middle term. I don't want a middle term, so I'm definitely going to use conjugates, which means 3, what I do to the denominator, I also do to the numerator, 4i. So I keep the same first and last. What's the difference? What's a conjugate? This was a sum, so this one needs to be a difference. Let's multiply these together. In my denominator, I've got 3 times 3 my first, which is 9. I do not have to worry about my outside and my inside. I know those are going to cancel out. 3 times a negative 4 will give me negative 12i. And positive and positive, I'll have positive 12i. So those will cancel out. I just have to worry about having done the first and the last. When I do the last, I get a negative 16i squared. In the numerator, though, I don't have conjugates. And those, I'm going to have to use my traditional FOIL method of 3. Then the outside, I've got a positive 1, a negative 4, negative 4i. Then I go to the inside, a positive 2, a positive 6, give me a positive 8i. And finally, I do the last terms, a positive 2 and a negative 4 for a negative 8i squared. Let me extend this so it's clear what I'm doing. I'm going to change my color on my pen for a moment. A negative 8i squared. I squared is the same as a negative 1. So this term here is negative 8 times a negative 1. I can actually re-express it as a positive 8. So when I go to write that, which I'll do it down here, I'm going to have a positive 8 and a positive 3. These are like terms. That'll give me an 11. And these are like terms. They just have I to the first power. That'll give me a positive 4i. In my denominator, my negative 16i squared is the same as positive 16. These are like terms, so my answer will be 11 plus 4i divided by 25. Find the reciprocal. Okay, reciprocal, I can do reciprocal. It's just like this. What's the problem with this? I hear you loud and clear. We want to rationalize the denominator. To do that, we're going to use conjugates. Anytime you're trying to rationalize a denominator that has binomials, it calls for conjugates. Otherwise, you get a middle term. So we've got 3 for our first. We've got 4i for our last. And instead of taking the difference, we take the sum. So numerator is easy to do. It's 3 plus 4i. And the denominator, because it's conjugates, I'm not going to have to worry about these outside and inside because they will cancel each other out. I just have to multiply 3 times 3, which gives me 9. A negative 4i times a positive 4i will give me a negative 16i squared, which I know from up here, right? We start right here. I know what that is. That's going to be 25. Why is that so? I square is equivalent to a negative 1. A negative 1 times a positive 16. No, it's not a positive 16. Times a negative 16 will give us a positive 16. Then you're going to have 9 added to that. Our numerator is already as simple as it can get. Isn't that interesting? So the reciprocal of 4i looks like this. Those are fun. They really are. Oh, and that's the end. See you in the next class.